Welcome everybody. Thank you for coming out on a Saturday morning to just for those of you who don't know me, I'm embedded systems engineer is what I call myself. Done hardware and software design my whole career, 9 years of professional robotics experience, mostly on autonomous full-size trucks, doing system test and calibration and hardware and software subsystem design. I've had 15 years of personal experience with ROS, past and present DPRG president and winner of the 2024 Robo Columbus competition, where my robot thoroughly slapped down Scott's, and he's very good at dishing out the slap down, so I'm giving him some of his own medicine and asking him to be prepared for the next one at 6 can. All in fun, Scott. So ROS is a set of software packages that enables compatible robots to navigate using ROS's map-based navigation with no programming required. Can you believe that? It's unbelievable. So I'm going to talk about just briefly what's ROS, what's Linorobot, which is a lot more interesting, and then some ROS navigation concepts, including SLAM and demos, which is really interesting stuff. Then talk about the Linorobot system architecture and how to build your own Linorobot. So Kareem, hey, welcome. So what's ROS? Most people, when they hear ROS, think of its plumbing and messaging capabilities and service request infrastructure, and it is that. It's an infrastructure that lets nodes, which are processes that process data, connect to one another in a flexible way using publish-subscribe model. And it is that. It's also, though, tools to let you visualize navigation, and we'll be seeing some of them. It's topics and messages, introspection, so looking at what messages are defined as, what they mean, and logging and playing back logs, inspecting logs for debug. It's a set of capabilities, including navigation, which is the focus of this talk, and path planning, both for arms and vehicles. But importantly, you shouldn't forget that ROS is a social ecosystem. So it's a community of developers and as well as adjacent products like OpenCV that's well integrated with ROS. It has a technical steering committee. It's an open source project. There's a discourse forum. There's a Stack Exchange for asking questions, a GitHub for collaboration and issue tracking, an annual conference. So it's really quite a big worldwide social system aimed at the production of flexible robot software. Presently, there are about 1,700 software packages that are released on a life cycle plan, so every year, and there's a CI, a continuous integration testing infrastructure that when you do an update to your package, you can submit it, and it'll go through testing to make sure it's compatible and works, doesn't break the build for the current, whatever current release you're on. So it is a lot more than plumbing and messaging service. So the ROS community is a big worldwide community headed up by Open Robotics. Open Robotics is the brand of the OSRF, the Open Source Robotics Foundation. Brian Gerke is the welcome. Brian Gerke is the CEO, has been since its inception. He was one of the creators and maintainers of a package called Stage. There used to be a robot simulation environment called Player and Stage, There were like 2 packages, and I think player was the robot simulation and stage was the environment. Anyway, Brian's PhD from Stanford, so well qualified to lead up open robotics. But then there's the community around open robotics. So open robotics looks after the core of ROS, its tooling, its infrastructure, but there's really organizations around ROS that are big enough to be really considered their own communities. ROS Industrial is one. They deal with ARMS, and they produce the Move It package that is all about, we're going to be looking at mobile platforms today, but they do that kind of thing for ARMS. The NAV2 community, we're going to be looking closely at their stuff today. Gazebo, the simulator that integrates with ROS. OpenCV is an adjacent one, and MicroROS, which is used in Linorobot, is a ROS compatible set of interfaces that runs on microcontrollers like ESP32, Teensy, PIC, I think. And then there's special interest groups, ROS Ag for agricultural space. OpenRMF is a group that deals with building interfaces so that robots can talk to infrastructure like elevators and move around. So, and then underneath all of that, contributors and maintainers such as myself. I'm now a committer on Thomas Chu's repository for Linorobot2. And so, people like you and me, and those of you, others of you who make software contributions. So what's Linorobot2? We talked about ROS. So Linorobot2 is a software platform. I think of it as a platform configured by a script and config files for wide hardware flexibility. I think of it as a platform much more than Turtlebot software or any of these other ROS software for a particular robot. It's a platform because it's general in a lot of ways, supports a lot of different types of hardware, which can lead to low cost. So user apps can ask NAV2 to navigate the robot somewhere on the map and avoiding obstacles as it goes, and that's what it'll do. And the Linorobot2 nodes fit in by helping the NAV2 nodes navigate through the map. So they provide things like the robot description, the interfaces to MicroROS, the firmware that drives the motor controllers, and the LiDAR, and so forth. So the two work hand in hand, NAV2 and Linorobot software. So in terms of hardware flexibility, Linorobot2 supports 2-wheel drive, 4-wheel drive, and Mecanum types of robots. ESP32 Pico Teensy in an Arduino environment for microcontrollers. Motor drivers, the standard PWM-based ones we have in A and B and an enable, like the L298, etc. Or ESC, so servo pulse-based motor controllers like you have that drive brushless motors. Motors should have a quadrature encoder. It supports LiDARs, a reasonably wide range of personal robotic level LiDARs, LD19, LD06, and STL27 over Wi-Fi, and then over serial or USB, the RP LiDAR range, the LD LiDAR range, ST LiDAR range, YD LiDAR range, and depth cameras. Fundamentally, ROS's nav stack wants to know where stuff is. It wants to depth to the objects it's looking at. And so you need some kind of depth sensor. And then a variety of IMUs there as well. So that's how I see Linorobot2 as a set of software that's configurable for a fairly wide range of hardware that can produce low-cost robots. So here are some instances of Linorobots. Of course, top left is my mini bot, but the other four pictures that I pulled off of the web at various places. And the idea of Linorobot2 is you build the hardware and it provides the software for compatible robots. Linorobot2 was created by Juan Miguel Jimeno, who's an engineer living in Singapore in 2016. He and others developed it over the 2016 through current period. They ported it to ROS2 in the 2020 timeframe. Thomas Chu has contributed a lot in making it Jazzy compatible and doing the ESP32 port in 2024. Here's about as cheap as you can make a Linorobot2. So you got to have a motor and some wheels. You just gotta. So, there's $18 right there. This is pretty cheap controller. This WaveShare General Robot controller with an ESP32 on it, which gives it Wi-Fi access to a laptop through your home Wi-Fi. And so the way you go cheap on a if you just want to play with it on a ROS robot is you run ROS on your laptop, which I'm doing here, and you run the microcontroller, have it Wi-Fi connected up to ROS on your laptop, and the micro ROS interface supports either serial or Wi-Fi. I've done it both ways. There's a little serial connector here that I used to have a Raspberry Pi 4 mounted underneath this. So you can go either way. No particular recommendation on which way you go, but this is this robot is currently on the DMS Wi-Fi network, as is my laptop. So one of the big ticket items is, this is a pretty cheap item, LD19, $60, but it's bigger amongst the price of things, and a battery, $20, and an IMU. There's a little IMU up here, and that's about all you need. $130 worth of parts, and you've got yourself a ROS2 robot that can navigate around in a map. And that's really what I'm explaining today: is how does that work? How do you use it?
What's the 350?
Good question. Thank you for that catch. So you'll see that there's a camera. There's a depth camera in front of the LiDAR. Optional. If you want to put one in, 150 for a Oak D Lite is what I showed there. And then the other one that adds bucks is there's a Raspberry Pi there under the WaveShare controller. So add another $80 for a RPi 4 with 8 gigs, or 100 for an RP5, whatever. So yeah, somewhere in that range is what you're looking at, depending on how you want to configure it. What do I want?
You get rid of the laptop and you make it self-contained.
Yeah. Yes, that's why you would put a Raspberry Pi on it, and that would be appropriate if you have a dodgy link. For example, all my robots are going to become Linorobots soon. The mower, when it's like out there, comms may not always be fast enough to want to run ROS on my laptop in the house. So yeah, that would be exactly why you'd.
You can make this
Absolutely. Just put a Raspberry Pi on there and off you go.
got enough power to run.
Yeah. I've run it, and Mike's run it, and yeah.
Doug, just a question. The Wi-Fi link, or the PC running ROS controlling the robot, that wouldn't necessarily meet the requirement of self-contained, right? In contest environment.
Yeah, most of our contests now, they don't have to be self-contained. That's been, that rules, and they changed on most of them. There might be one or two out there that I don't know about, but at least even 6 months now is no requirement for
Right. Robo-Columbus still, but, oops, I kicked it out.
Yeah, so
Mechatronics, what does that mean?
one of my biggest problems is I don't
That's
want
what you are.
someone that has a laptop
Look it up.
talking to something. I don't want.
I don't understand. Okay, you can understand me later.
Look it up on Google.
Okay.
And somewhere between RC and.
Yeah,
Yeah.
I agree. Right.
I'm
Okay.
good. Final product, enough power to be able to do it.
Saying, Raspberry Pi, what?
Raspberry Pi 4. I usually use 8 gigs just to be safe.
Yeah, this there are significant differences between the Raspberry Pi 4 and the Raspberry Pi 5. And is the software caught up to Raspberry Pi 5?
It has now. Yeah, several people are running ROS on Ubuntu 2404 ROS Jazzy on Raspberry Pi 5. So yeah, it has caught. It didn't used to be caught up, but it is now. And let's see, I'm just gonna plug this in until we need to. But there are other options for a ROS2 navigable robot. The Turtlebot 4, you can get in a light and a regular model. The regular has like a big thing on top of it. I don't know what's in it. But it's the canonical ROS2 robot. If ROS doesn't work with Turtlebot, ROS is broken. But it doesn't use micro ROS. It uses the robot motion control and sensing is done by the Roomba iCreate 3 with a serial connection to the iCreate interface node on the Linux PC. So this is a specific hardware implementation with limited hardware flexibility. Assumes an iCreate 3 base and specific sensors out of the box. You can always hack that, and there's some guys in the Homebrew Robotics Club that are hacking Turtlebot to use different bases, different sensors, but then it's no longer turnkey. Okay, so that's why I differentiate between the specific hardware implementation and the general build your own robot implementation. And that runs 2K for the full-blown one, 1300 for the light. Maker's Pet plus KAIA.ai is a new entry. It looks like they're just ramping up, intending to produce their first product first half of this year. Maker's Pet does produce that robot on the right, top right, and supposedly it will work with KAIA.ai, which is a very Linorobot2 like software stack. Comes with Docker containers and the Docker containers can be run on Windows. So it's a very Windows friendly environment. Again, it's going to be turnkey for a particular robot. I'm sure there's flexibility there. You need to dig into the Docker containers and see what's in them and adjust it. We'll be going through the Linorobot configuration steps here a little later, and you'll see how straightforward that is. Yaboom is featured in advertises itself as a ROS2 compatible robot. Features in a great set of tutorials by Automatic Addison. Automatic Addison is this guy who does these fantastic tutorials, both video and written, that show you how to use ROS in all kinds of ways, take you from a Linux beginner to a ROS beginner to really doing ROS navigation and understanding how it works. It's got a huge and fantastic set of tutorials. Don't know anything about Highwonder or there's AliExpress robots or how they stack up. So looking at Linorobot2 in the package context, in the context of other ROS packages, starting at the bottom, you've got hardware at this green layer down here. The ESP32 running micro-ROS in Arduino comes in a repo called Linorobot2_hardware. Just download it, you use Platform.io to build it, you configure it, and we'll go through how to do that. Other hardware devices live below the network layer, may use the network or may use direct serial connections. And then you've got ROS nodes above that, hardware dependent layer like the micro-ROS agent that talks over the link to the micro-ROS in Arduino and publishes topics up into ROS, transports, drivers for all kinds of hardware. So, and then above that, I think of a nodes layer, all kinds of nodes that just do everything you can imagine. And above that, the term meta package is a little bit old-fashioned, but the concept is a group of packages that do something. In this case, there's a Linorobot2 repo that contains a group of packages related to Linorobot. Turtlebot has a group of packages. Nav2 has a group of packages. MoveIt, the ARM software, has a group of packages. So this is, and then above that you have the user apps. And then to the right, you have related software systems, sometimes with bridges to them, to like Gazebo has bridges between ROS and Gazebo and OpenCV. So the nodes do the work. The hardware-dependent nodes expose specific devices to ROS. Index.ros.org lists 1,700 packages, and someone discovered 2,700 repos in GitHub tagged with ROS. So it's a big software system. So you should expect to deal with a large software system if you get into ROS. But you know, that being said, don't run for the hills, because you already do deal with large software systems like Windows, Linux, Python. Arduino has, it must have 1,000 packages, but when you consider all the community contributed packages for this. Yeah. I mean, these are big software packages, and you find typical problems of incompatibilities between different versions of software, and you just have to work through the issues. But I'm just setting your expectations about
The network on here, that could just be DES on the PI, right? The
Yeah,
network layer
yeah,
doesn't have to be
yeah.
Wi-Fi.
Right, yeah. So this is a Linorobot system design. Oh, I just want to make one additional point about the Arduino environment of ESP32 running micro-ROS in the Arduino environment. That is really important because it means you get access to all of the ESP32 community contributed packages. And I actually used it for the servo that runs the claw on this. I was like, well, there was no servo software in the Linorobot package, so I just found ESP32 servo on the Arduino, compiled it in, and hooked it up to a little programming to hook it up to a topic, and now it accepts servo position commands from ROS. So that's just to say Arduino means a lot when you say it's Arduino compatible in the ROS environment.
ESP32 could be RP40.
Yes, exactly. Yeah, yes, exactly. So it's an important point. Okay, system design. So there are variants, the off-board computer running ROS and the onboard computer running ROS. This drawing shows an onboard computer, a robot computer with the laser scanner driving straight into the robot computer, and a microcontroller that's USB connected with that drives motor drivers through PWM digital pins and reads encoders through interrupt pins, and has an I2C to an IMU. If you're in a Wi-Fi configuration where your laptop is your robot computer, then you're a little more restricted in terms of laser scanners, because you need to have something running on the microcontroller that can talk to the LiDAR and then ship its data up across the network, across Wi-Fi, to your laptop. The way that works in Linorobot is there's a this is like a general architecture, but you got this little cable here that goes to a designated port here, which goes to one of the I/O ports on the ESP32, and then there's a little section of the microcontroller code on the ESP32 that expects LiDAR data and pushes it up into a UDP socket headed for a laptop, and you configure what the IP and the port number that it should be sent to is. So not difficult to generalize that to other Wi-Fi implementations. So that's the hardware design. Here, this is the software architecture. So the ROS nodes run on the robot computer, and so that's the upper half of the diagram here, where the ROS2 agent is the thing that talks across the network or across USB serial, depending on whether you're Wi-Fi connected or not. And it accepts messages on the command vel topic, which are the robot motion commands. So command vel contains twist messages, which have a linear speed, requested linear speed, and requested angular speed. So that's how ROS, whatever's up there in ROS land, asks the robot to move. The ROS agent also publishes odometry on /odom unfiltered, which feeds into an EKF filter that fuses it with IMU data, also published by the agent, and emits transforms and the odom topic. Down on the microcontroller, you have the micro-ROS library that interfaces across the serial or Wi-Fi link and publishes these topics or subscribes to these topics. And you have kinematics, the PID, the motor driver, the encoder driver, and the IMU driver. So that's the hardware and software architecture. Any questions on that before I move on? The LiDAR would be, so for the Wi-Fi configuration, the LiDAR goes into this bottom block here. Actually, there's a separate, the LiDAR is not shown on this drawing. For the Wi-Fi configuration, there's a separate piece in the firmware that takes the serial off the LiDAR and pumps it up outside of the ROS environment, outside of ROS messages or anything like that. Just pumps it up through a UDP socket to the laptop. If you're running on the robot, then it would plug into a serial port on your robot computer, on your Raspberry Pi. And then you have a LiDAR driver for whatever your RP LiDAR is or whatever, and that knows how to initialize the LiDAR and tell it to start scanning and publish its data into the ROS infrastructure.
If you lose your IMU, you still operate manually, remotely control.
You can also, yes, you can teleoperate. You can right. You can teleoperate it. You could even operate it without the IMU, just off of odometry. Well, you
Go this far and then
That-
this much and then go that far?
that's a really good question, and a really deep one. So the NAV2 stack, so this balloon, this hot air balloon, is the NAV2 stack, and it's really centered on the idea of navigating within a map and taking LiDAR and localizing the robot and planning path planning and that. So if you don't have LiDAR coming in and you don't have odometry, what do you have? Well, you could make your own navigation package, as I've done, what I used for the Robo Columbus robot that navigates between waypoints, and many of us who've built have built Dead Reckoning robots. But at that point, you don't have NAV2 in the game. Why do you even have micro ROS? Maybe it's good because ROS is like a nice interface to sensors, but
Well, it easily supports steering where you could have,
yes, and I'll talk specifically to that point a little later on. So hold that thought because I'll get there. Okay, so micro ROS. It surfaces topics, and let's see. Let's just see where I want to go with this. Okay, I think what I want to do is, just for the sake of a demo, I'm going to. So I've got an alias for this Minibot Wi-Fi bring up, and this is the alias. I'm going to copy that, and if you look at the parts of it, you ROS2 launch Linorobot2 bring up. So this is the robot bring up running on the ROS side in the laptop, giving it a launch file of bring up launch.py, telling it parameters. The micro ROS transport is UDP4. The micro ROS port is 8888. So that's what it should communicate on to the micro ROS port. You would give it a serial port specification if you had USB serial to the robot computer. And there's a wiki that tells you how to do all that. And then the LiDAR transport is a UDP server with a LiDAR server port on 8889. So let's switch over to, I'm going to Control C this, and okay, so we're going to run that exact command, and it spits out a bunch of stuff telling you that it's starting up, it's got LiDAR running, and then it's creating publishers and data writers and subscribers. So this is where, so I've just, one of the things done by this launch file is it publishes it starts the micro ROS agent. And so the agent is now publishing topics on ROS. And we can do ROS.
Well, this is all on your laptop.
Correct, but it's talking to micro ROS on the.
Has opened the ports.
It has opened the ports, and it's talking to micro ROS on the ESP32.
ESP32 is already booted up in this
Right.
on the network.
Exactly. In fact, we can tell you what we'll do. We'll go one better. We'll power it off. No magic here. And then and I'll just show you one more neat thing. So Linorobot2 is capable of publishing to syslog on a laptop. So let's tail -F slash /minibot Wi-Fi message hardware.log. The last time so this is what was left in the log. So we'll power the robot on, and we'll just sit it down here for grins. And okay, so after there we go, we've got a Minibot Wi-Fi hardware setup ready at time 13:046. So so I'm looking at the syslog here. So the microcontroller opened up its Wi-Fi, connected to DMS Wi-Fi, sent a syslog message up to the the syslogger is always listening on Linux, and I'm tailing it, and up it came. And so now let's start up our. By the way, are you guys on the call seeing my screen?
Yes.
Okay, great. So let's launch the Linorobot bring up script that starts the micro-ROS transport, and then we'll flip back over to the. Okay, so we've got a new entry here saying it created entities at this port. So we've started up the micro-ROS agent now, and it's talking to the firmware, and we can do ROS2 topic list. And so the agent and the other nodes that were started by the startup script are publishing battery, subscribe to command val, publishing diagnostics, IMU data, and we can do a ROS2 topic echo / battery just for grins. And we should see a battery message coming up from the robot every now and then.
So we back up a step. When you brought up the robot and ROS on your laptop, it started publishing the syslog. So those syslog events, did you have to define them, or they're like defaults that the systems are?
They're in the firmware code. So the firmware just. It's built to where you just do, I forget, there's like a microcontroller version of log printf, and so it's just whatever that firmware prints is what comes up across the link to go into your syslog. Yeah, it's pretty powerful. So
you still had to point the robot to your left.
Yes. And I'll go through that when I go through robot configuration. But yes, you do tell it where the syslog server lives. Otherwise, it wouldn't know where to send it. Right. But it's still, there's pretty good magic here, right? So what it means is when you're developing, like putting your custom hardware servo drivers or whatever, you can put printfs down in the firmware, and they'll come up through the syslog mechanism and turn up in your syslog on your Linux box. Pretty powerful. Okay, let's see. Other so we'll be printing lots of data on scan and ODOM. So right now, what's running is the ROS2 agent, this EKF robot localization node, the TF node that's publishing the location of the robot, and odometry is coming out of the EKF node. So it's just sitting there. That's all that's running at the moment is 3 or 4 nodes in the ROS land that are getting data from the robot and ready to send data to the robot. Okay, so now we can do things like send a message. So one of the topics here is /servo. So that's a subscriber that I just configured down in the down in the firmware, listening for a servo command. So we can send it a servo command to tell the servo to go to 1100, and probably nothing much happened because it's already there, but let's send it to 1400. Why is it not working? Why is it not working?
Oh, God, strikes again.
Oh, I remember. This is a little fragile. I had to rip the closed. I had to rip the ends off of the connector to get this servo connector to fit on the connector. So it's a little janky. It's more than a little janky. It's very janky. There we go. Hey, you guys thought you could scare me? No way. So anyway, evidence that the servo topic that I'm publishing to is making its way down through the ROS infrastructure into micro ROS, reaching the Arduino ESP32 driver that I compiled in, and it's good stuff. It's just the default for the ROS2 topic pub. Didn't used to do that, but it does now. There's an option that you can give it. I think if we give it the -1 option, it'll send it once. Jason? Jason? Ed. That's right. Sorry, I knew you, and I was like, okay. So I want to say a few words. I want to get into some conceptual notions about navigation in ROS2 and how ROS2 thinks about navigation. Do we have a video camera somewhere? Oh, okay. So the primary goal of navigation is to move a robot from point A to point B, pretty obvious. Hopefully it can sometimes respond to obstacles. ODOA is what we call obstacle detection, obstacle avoidance. And, but that's optional. In competitions like Foursquare, we just assume there's nothing in the way, and if the robot bangs into something, then you pick it up. But you can think of level 1 as being dead reckoning navigation, where you're so if you were like in Robo Columbus, you can use dead reckoning navigation if you've got GPS. I haven't seen anyone be successful with it, but Foursquare and Quick Trip definitely dead reckoning. Just count the odometry, go out there, turn around, come back. That really doesn't work when you've got rough terrain like in Robo Columbus. Never seen anyone come anywhere close to succeeding with odometry on. But, okay. Oh, you're right. He is. You're right. Yeah, you're right. Thank you. Yeah. Really? Wow. Okay. So I think of level 2 as being navigating within a global frame, like with GPS, where you go between waypoints. I think you and Mike use a global frame for 6CAN, where you localize within the arena, so the robot knows where it is. And so that helps a lot. It eliminates drift and initial heading issues, but the issue is the route has to be manually planned, which is a lot of work if you're dealing with a complicated route like going from here to Dallas. And the level 3 is navigating within a map that's in a global frame, like Google Maps driving to Dallas, a robo-vacuum in your house that's made a LiDAR map, SLAM map of your house with automatic path planning. So level 3 is what Linorobot is focused on, and that's the focus of this talk. So let's think for a moment about what is a map really. It's a 2D representation of the environment, right, with fixed obstacles like walls and furniture and road boundaries, possible destinations like kitchen and bedroom, and navigable areas with some resolution. So the default in nav2 is 5 centimeters per pixel. This top right drawing is a picture of the Google Maps, the Dallas Makerspace. The map has a value at each pixel that represents something like navigability. Gray means navigable. Yellow means not navigable in Google Maps. Down at the bottom picture is a SLAM generated map of my hallway. And white means navigable. Gray means unmapped. And black means obstacle detected by the LiDAR. And we'll make a map today, I promise you. So the issues that you have to deal with map-based navigation is how do you make the map, how do you plan within the map, and ODOA. Because the map doesn't include dynamic obstacles like when we walk in front of the robot and it has to alter its path. Or there are hands there placed strategically. So there are well-known algorithms for global path planning within a map, and that's all in the nav2 stack. ODOA is handled by the local path planner, which plans deviations from the planned global path to avoid obstacles. And we'll see that here going in a sec. So we're going to make a map right now. We're going to demo SLAM with Linorobot. Okay, so we're going to launch out of the Linorobot 2 navigation stack. We're going to launch SLAM and ask for RViz to start. And what we're seeing here is the LiDAR reflections.
Okay. Yeah, there you go. Okay.
So we'll, at this point, what I'm going to do is drive it, teleoperate it. Oh joy. And what you're going to see is, as it drives down the hallway, you'll see the LiDAR pick up more space. Now, it's making a map as it goes, so we can also get it to drive itself within that map.
Give us a basic spec on the LiDAR. Is it, I assume that's the LiDAR on top.
Yeah.
And
It's doing a 360 degree scan.
360-degree scan.
Yeah.
And elevation, is it 108?
No, it's just a beam, just a beam LiDAR. Single beam. Yep.
Okay, wow.
So yeah,
That's
you
like
have,
running the
like that here,
below it.
yeah.
I figured you could see up some elevation as well. Okay, so it's a single beam.
So this guy's seeing what's 4 inches above the ground.
That'll explain a lot if you understand what running.
Yeah.
Right. Okay. Although this looks sure a little bit.
Yeah. So it detected a couple of dots from Doug's feet. See these black dots here? That's Doug's feet when he was standing there obstructing it. That Doug guy is obstruction. Okay. Yes, yes, and thanks. I didn't mention that, but that's so where you see black here is where it's determined that there are obstacles. So here's the obstacles for this front. Well, there's your LiDAR. Now it's not creating an obstacle right now, but that's you. But it's not moving and trying to make one. I can't tell you why it's not. I can't tell you the exact condition that causes it to make or not make an entry in the map. But I'll tell you the black dots. You can see two of them here, two of them here. Those are the chair legs. The pink and the colored squares are the LiDAR reflections from what it's seeing. So now we're going to save the map. So let me get back to the instructions for saving the map. Yeah.
So those obstacles that we use, that now is rescanning and seeing that it isn't there anymore. Can you have that then removed from the map?
Once they get into the map, they stay there. But you can clean up the map with an editor, a graphical editor, and I'm going to show that here in just a sec. So first of all, I'm going to run this map saver command. So this will read the map as it currently exists in ROS's map topic, and then save it away as a file.
Any way to change configuration on some of the decisions that the map makes, though? Like, if something's there and then it's not there, it's the criteria for determining something right. Yeah.
You have to look at it and decide if you think it's right. Okay, I'm going to call this DMS2.
I think it's simultaneously doing mapping and navigation.
Yeah.
So this is basically making a map and then coming back and then doing that. So it's not quite what I think of.
I disagree. I disagree with that. You are correct in the sense that it's not navigating within the map. I'm driving it within the map. I tried to let it navigate within the map, and it got itself confused and lost its localization. I found that to be a bit fragile, to be honest. But it sometimes works, but the demo effect happens. Yeah.
It does not remember the map.
Right. Right. Well, but it does.
It does if it's in a run, but not, if you turn the robot off and turn it back on, it's starting.
No, my Xerox has a map of the house. I can bring it up and show it to you. It's like map the house out. It goes on an exploratory run, explores all the rooms, and then remembers them, saves them away, and you can post-process it to put in like label rooms, put in dividers between rooms. It's pretty sophisticated.
I'm just saying when I looked at Nita, it was doing.
Okay, yeah. So I'm going to save the map here, but I think a point worth. Okay, so this will be the map that we'll save, and wherever there's black dots will be what saves.
Would this be completely unaffected outside then?
Depends on how good of a LiDAR you've got.
Yeah, I was going to say a lot of this, when you talk about the limitations, is really based on the configuration of the equipment.
Yeah.
You had more ground clearance with LiDAR underneath
Yep.
the legs of the chair that are close to the ground.
Yep.
Well, I mean, even if this room, these chairs are real nasty because they have a bar.
Right, that's what I mean, that bar and bottom.
So,
Yeah.
won't say a bar.
unless you had one with more ground clearance, you had a LiDAR on the bottom, but,
You know,
or on the side that was downward.
They want to see the, you know, where it's set up on this road, they want to see which part.
Right.
But, you know, that's true of almost any of the sensors that we use. I mean, that's, I mean,
Okay, so I want to keep moving here.
That's very much configuration.
yeah, of the road.
So,
Well, not all LiDARs are set up the same too. A lot of LiDARs, you only get things, samples in a scan.
so let's keep on track because in half an hour pizza's going to come, and I'd like to kind of like get to some kind of conclusion here. So I've just brought up the map that we just saved in GIMP, and we can hand edit it. I can erase. Oops, I want a smaller brush size. There we go. We can just erase Doug's feet. Doug is now gone. Bye-bye, Doug. And we'll export that as back to dms2.pgm. Replace it. Raw. So that's more of a conceptual question. That question really comes down to why do you want a map in the first place? Because if you can make it anywhere you run, then what's the point of having a map? The idea of a map is it contains data about the environment that can be used for planning, about possible regions, about which area you call a kitchen that it should vacuum. Yeah, right. So you could drive it around and it can navigate within the map as it's going, and you can tell it where to go. But and in fact, that is how the Xerox works when on its exploratory map, because it's driving itself along and it just takes a left turn at every doorway and turns in, maps it, then it comes back out, goes to the next room. So yeah, you could do that, but then you're losing the value of having a map as being something that has additional information in it that can be used for navigation.
So would it be a different system if you're just wanting it for obstacle avoidance, maybe trying to determine if it's a doorway or if there's a wall as it runs?
You don't need a map.
Okay.
Right, right,
And for
right.
That's why a lot of robots don't map, because they're interested in figuring, we're going to go hit something, can I get the point X? Map, it can tell you where you get the point X. It can tell you where you can.
Or route, a non-direct path to it. Like if you wanted to go to the room next door, right, without a map, you'd say, well, I'll just go straight across here. Now that we have a map, now you know there's a wall there. So now the path has to go around that wall.
Okay. So the map has value, but you don't, outdoors, map kind of goes down because.
Yeah.
No, we do.
What have you?
something similar.
Yeah. Where are you? Where are really the significant things? So a map is not necessarily appropriate for like things like Robo Columbus. It depends on what you're trying to accomplish.
I think some of the concepts are the same though, because like in Robo Columbus, all of us mapped the different coordinates. We didn't go straight to the pump, right?
Right, right.
So we were adjusting the map, the course, based on the map that we visualize, not necessarily one that.
It's a map in our brain where we put down waypoints that correspond to points in our brain. Here is where you have a map that's actually in the software as a data file that it can navigate around. And
What if you put this in you wouldn't see the wind. It's a range of
Right.
people.
Right.
So it would just.
Right.
But in my approach on in Robot Commanders, you could go to Google Maps and the location.
Yeah.
Half out areas you do not. So in a sense, you're creating malls.
Yeah. So SLAM works by tracking the relative motions of key points in the LiDAR scan, and discovering more points as it goes. But if it loses localization for the IMU and odometry, which is what happened when it charged into Jack's chair, then it can discover new LiDAR features that it lost track of, or it was tracking previously, but now it thinks they're new, and it makes a wrong map. And so that's why I had to kill it and restart and redo the map. Okay.
Does that mean then that the map you just saved and edited in GIMP, which you would load back into the robot, does that only make sense as long as the robot hasn't moved from the time you downloaded and saved it?
No, well, I'll get there. So hold that thought. But I want to introduce two new concepts: a global cost map and a local cost map. So they call a map a cost map in robots, because there's the data that's at each pixel in the map represents a cost to navigate. So the global cost map is used to generate long-term plans over the entire environment to go, from A to B, whatever A to B is, to figure out the shortest point, or at least the most feasible point. So you create the map with SLAM, and it's used by, or an editor. You can just create a .pgm file with GIMP and at 5 centimeters per pixel, make yourself a map of like the 6CAN course arena, and you got a map. Black is not possible. I don't know what value, and then that's a value of 254. I don't know what value represents unexplored versus clear. And then other intermediate values represent the cost of navigating. And what it will tend to do is put a higher cost close to walls. So it tends to create a potential gradient that causes the path planner to navigate in more clear areas. The local cost map is used to generate short-term plans over the environment to avoid obstacles. And it's dynamically created from LiDAR, and it's used by the local planner. And the two cost maps need to be aligned. And what can happen is if you lose localization, the local cost map can end up twisted relative to the global cost map. And then you got like LiDAR detecting walls that actually go across clear space in your global cost map. So that's one of the things that can happen during navigation.
That's maybe what just happened there.
Yeah. So a little bit more ROS navigation theory, and then we'll move on to demonstrating navigation. ROS uses the concept of coordinate frames. So someone asked about frames. The pose is the position and orientation of something within a frame. Could be within a frame within a frame. So the LiDAR has a pose within the robot frame. So it has a certain position, so does the IMU. It has a certain X and Y offset relative to the robot center, and a certain height above it. So the laser link and base link are well-established names for the center of the laser, the center of the robot base. And then the base footprint is just the point on the ground immediately under the base link. The odom frame is the frame that odometry reports in. So when you turn on a robot, it says I'm at 0, 0. But what does that really mean? It's within the odometry frame. But the odometry frame has some position within the global frame. So here I'm showing, which is called the map frame. So the map frame is really the global stationary frame that nothing moves, nothing in it moves. The fixed obstacles are the obstacles. The odom frame can be moved, and I'll explain how that works. And definitely the robot moves within the odom frame. The robot also moves within the map frame, right? If it moves a meter forwards in the odom frame, because it says, my odometry says I moved a meter, but it only moved 90 centimeters in the map frame. Let's look at how this works. So let's start with the right-hand side of this picture, where the laser detects a wall 0.3 meters in front of it. Now, in the middle frame, we see that the LiDAR is 10 centimeters from the center of the robot. That means the wall is 0.4 meters from the center of the robot. And so if we had started this robot at the odom frame at 0, 0, and that was 1 meter from the map frame, and we drove it 3 meters, that would mean, and now we know that the wall is 0.4 meters in front of the center of the robot. That means the wall is now 5.4 meters in front of map, right, in the map frame. And so here's how localization works. The LiDAR is spinning around, seeing where the wall is and any other points. The robot localization software is looking at the map and trying to match those LiDAR points, those LiDAR features, against walls and other obstacles that are in its map. And then, so what happens if we asked our robot to drive 3 meters, but it only drove 2.9 meters, you know, LiDAR knows that because, well, the software monitoring the LiDAR output and comparing it to the map observes that the that the robot only drove 2.9 meters, but odometry says it drove 3 meters. So what the software does is it moves this odom frame within the map frame. It pulls it back 10 centimeters, so that now the odom frame has moved a little, but all the math works. The map to odom is now 0.9 meters. The wall is actually 4.3 meters away from the map origin. Okay? So it's tricky stuff. I mean, this is like PhDs, right, discovered this stuff and wrote software. And
I thought that the odom frame just moved for localization, and it's a 0 point of a point on the map, and it moves it around just to keep it in position. It doesn't, like, the odometry doesn't move the odom frame. The odometry only moves the base.
Correct. The odom measurements, the odometry measurements off the wheels, only move the robot within the odom frame. But the robot localization that's looking at the LiDAR and trying to localize the robot in the map moves the odom frame to put the robot in the correct position. So it's as if you've got like overlaid. So if you've got the odom frame here and the robot frame, and it's got the map here and odom here and the robot here, and then the robot moves a bit. You can think of the odom frame moving with it, but maybe sliding across the odom frame may slide across the map frame.
Last mapping out, I was looking at the Odom frame and it was because of drift.
Yes.
It would drift around.
Yes, it absolutely will. And I'll tell you what, we'll actually look at that. I've got that as part of the demo. So instead of doing drawings, let's go straight to the nav demo. So, okay.
And the name Odom doesn't mean that geometry is that. Odom is geometry. Yeah. The drifting and geometry can follow.
Okay, so let's.
Right.
Then it'll be able to find the map. Map con equals DMS2.yaml. Okay, so the question was, how does the robot know where it is initially? We tell it. So it's going to be approximately, so I'm going to click this 2D pose estimate, and I believe it's just down about here. And so we'll see if we believe that. Not terribly. Somewhat. So, yeah, it'll fix itself up. It's surprisingly resilient. But you can see, if I turn the controller off, you can see so this is the global map we're looking at now, and see how it's like, you can see the LiDAR hits that detected the table legs, and there's a red tinge around the edges. That's the potential gradient that it's injecting to cause the planner to keep away from obstacles. Now, as I turn the controller back on and we see the LiDAR scans, you'll see that they somewhat overlap. The pink points are the LiDAR scans. If I gave it a whole different pose, say tell it, you're over here, then there's not much black that's kind of like being overlaid by pink. The two frames are not well aligned here. So you want to be kind of as aligned as you can. Where was I?
Is it more cautious around if it's closer to the obstacle?
Yeah, it'll slow down. It'll slow down. I'm still in the wrong place. I wish I hadn't done that. There we go. That's kind of there. Okay, so after a while of looking at a map, you'll get to recognize where the walls are. It's a bit difficult here because we've got table legs that are hard to understand what exactly we're looking at on the map, and the LiDAR. But so let's navigate to here and see what happens. This is a nav2 stack is what's doing all of this. Did I tell it what? It decides what path to use. What I told it was what pose to go to. So let me do that again and watch the screen this time.
What it did was it turned around because it had to go that way.
Right.
But if you originally started pointed this way, when you got up to David, it had to get front pointed the same direction as it was here.
Only because I told it that's the pose I wanted it to have. So let me show you one more time and watch carefully here. I'm going to select the nav goal, and then I'm going to click on where I want it to go to, and drag. See, I can ask for it to be in any pose, pointing in any direction I want. But I'm going to ask for it to point in the direction opposite to where it was coming from. And so now see this pink line? That's the path that was planned for it to go on. Yeah, it continuously replans it.
So like right here, it's not that it's skewing off course, it's just the
Right.
plan to get it.
Right. Now, let's get a little more adventurous. Let's put some obstacles in the way, and let's ask it to navigate up here, so near the front of the room, point in the opposite direction, and we'll put and watch the path here as I put some obstacles in its way. It's detected them, and it's said, "Oops, I'm going to So that's it. Oh, it didn't have time to plan around that. It might have escaped.
Could it be that the gradient was too high because things were too close together and it would make it through? Unsure. Good question. Okay, so yes. Sorry. Okay, I'm going to do one more ROS demo, I think. One more navigation demo. This is the, there's a feature in RViz for waypoint following. So you click this, if you click this waypoint through, I guess we're still recording, okay. Click this waypoint through poses mode button, then you can define a sequence of nav2 goals. So I'm going to define 2 goals. One of them will be down here a bit ahead of where the robot's pointing right now, but pointing in the opposite direction. And it leaves a little arrow there pointing to the waypoint. So that's a waypoint pose. It contains both the position and the desired orientation of the robot. Then the second node I'm going to place up here. I think this is the right place, hopefully. And then I'm going to say start waypoint following. And with any luck, it will head off, okay, towards the waypoint, and then turn around and face in the requested direction. Oops. Okay, now look what's happened. It's lost localization, and the local cost map has completely drifted away from the global cost map, and that happens sometimes. Happened to Mike, right, in 6CAN. If I zoom in, see this what looks like little green fuzz around it is actually arrows. And so it uses an algorithm called Adaptive Monte Carlo Localization, AMCL, which spreads a particle field around the map, and for each point in each particle in the cloud, it says how does the LiDAR data line up with this as a candidate position, and then as it's driving along, it's like continuously reevaluating all of the points in the point cloud to say, does this, where's the most likely actual position based on
based on each of the points. And so that's why you find a cluster of points. So, okay, so now to your question about the API and could you tell it where it is? So nav2 wouldn't be much use if it required RViz to use the robot. You know, you really need to be able to program it to do whatever your particular job is. And it has an API for user apps. And all you got to do is just a little programming. But here's some code that actually works. And I'm going to try and use it. Try and demonstrate it. It may or may, my mileage may vary. But what the code does is a Python app. There's an example. I've got a link to the API in the references in the slide deck. It initializes the ROS subsystem in Python. It instantiates a basic navigator. It tells the navigator to wait until nav is active. Then it defines a pose, as this being a goal pose, and says what frame it's in, sets a timestamp, sets a position to 0, -1, and I've just got orientation W and Z. These are two elements of the quaternion set to some, you know, whatever. I don't care what the final pose is. Then you call the navigator with the goToPose, the navigator's goToPose method, passing in the goal1 pose. And then you try this, and the reason it's in a try except clause is because you want to be able to Control C and stop it if it you know, you see it's like lost its localization. So while not the navigator says its task is complete, get feedback. And so it'll sit in this while loop until it gets to where it wants to go. If you give it a Control C, then it was interrupted and cancels the task. And then finally, depending on the task result, it says it either succeeded or canceled or it failed. That's all it takes to have a programmatic interface to the nav stack. So here is the pièce de résistance, and this is for you, Mike. Look at this diagram. You can have your user app, you can have your joystick, and the user app can give commands. Stop. The user app can give commands to nav2 to say, go somewhere, like to a goal area. Then it can give commands directly to the micro-ROS agent by publishing on the command vel topic to do something useful to you, like approach a can or a cone and grab it, or whatever your task is. And then it can hand back to nav2 and say, go somewhere else. This is brilliant.
Are you saying in the middle of navigating to a waypoint, you could say, wait a minute, let's get the joystick and...
No, not in the middle. Not in the middle. You can ask it to navigate to a waypoint, then you can take over control of it. So it's sort of like your friendly Uber driver that's just sitting there watching you move, watching you drive, and ready to step in and drive somewhere. And so, the scenario I'm trying to explain is not in the middle of navigating, but you have a job that tells your robot to go somewhere. It arrives there, and you get a feedback through that feedback mechanism that the task is complete. And then you can send direct motion control robot motions to your robot, maybe sensing your senses and looking for a cone or whatever it is that you want your software to do. Drive the robot through your user app here, till it's done whatever it was supposed to do, then say, hey, nav2, take me somewhere else. Return home, you know, whatever the application demands.
Do give you clothes, and then your computer app would have fine points.
Exactly, exactly. I mean, it's brilliant. And so I'm going to hopefully demonstrate that.
Then you grab a can, and then you go to navigate and say, go to goal.
Right, right,
And avoid obstacles.
right. So let's see, I'm in the wrong window.
I guess that the Nav2 API lets you pause it or cancel it or
Yeah.
interrupt it.
Yep. Yeah, so here's a navigator.cancel task method. So you can, so while you're polling it, getting feedback, if you decide, so this would be one way, you know, we talked about recovery mechanisms in case it gets screwed up. You could go and say, okay, cancel a task. Now let me look at the odometry and link with it. I believe the odometry more than the LiDAR. So let me set the initial pose to something different that compensates for it being messed up, and then carry on. So, you know, a lot of power in this API. Yeah. Now, so what I want you to notice here, I'm about to drive it. I hope my Joy program is still working. Yep. So notice that it's moving the cost map along, and the LiDAR obstacles are sliding alongside it. So the key here, okay, it's not in the right place in the map because it just drove over a bunch of obstacles in the map. But the point I'm trying to make is Navigator is sitting there just monitoring the system, looking for where it is, trying to match up, trying to localize it as it's moving, as something else is moving it through the environment. So it's like your Uber driver, just sitting there watching where you're driving and keeping a track of where it is on the map. And then at some point, if you decide you want to take over, you want to stop driving, you want to give it to it, then it knows where it is and it can go somewhere else. It's magic.
Does it have a sense of how confident it can be in its current mapping of the local frame to the?
Really good question. I don't know of any kind of measurement of that.
100% confident right now.
Really good question. I don't know the answer. Okay, so that was the main point that I wanted to bring out, is that it's sitting there localizing itself even while you or your app are driving it around. And so you can hand off to it at any point and say, okay, now I'll give you the job of going back to the goalpost or whatever you'd like to be done automatically while it avoids obstacles. And then when you get there, you could, you know, do whatever you want to do. Maybe you open the jaws and do a backup directly to the robot. Then you tell it to go somewhere else.
I know the driving primitives were acting sort of like it was doing 3-point turns as opposed to knowing that it's a differential drive robot.
Right. That's a really good question. That's a parameter you can tune. There are over 100 parameters in the navigation stack that you can tune, and the preference for forward versus reverse driving is one of them. I've just left it as the default, which seems to me like it might be set up for Ackerman type vehicles. Don't know that for sure, but that's my guess. All right.
Does ROS have a built-in user interface or ability to develop user interfaces, or is it command line?
No, it's got a bunch of tools, bunch of graphical tools and command line tools. RViz is one of them, but there's a bunch of others. RViz is what I've been using to navigate it, yeah. But it's got a bunch of them. Okay, so that was what I think is, I just realized that a day or two ago about how it tracks itself. And I thought, darn, that's brilliant. Okay, so here's a workflow for making a Linorobot2. So this is how you can build your very own one. Here's the URL to the wiki, Thomas Chu's wiki. On the right hand, I'll pull this file up here in a minute, and we'll go through it in a little more detail. But the overall flow is, he recommends, first of all, install the software. So ROS Jazzy, the Linorobot2 repos, and test micro-ROS agent connection before wiring and building the robot. And I actually did that. You don't need to have any sensors hooked up to it. You just, like with the default config, you just like get any old ESP32, download that firmware onto it, and then start up the agent. And if they're talking, you'll get like topics published, and it'll say it created subscribers and all kinds of stuff. So get the software and the firmware talking first. Then connect the IMU and run test sensors. So he's got a bunch of exercise programs like print the IMU output, and he has you shake the robot and make sure the IMU readings are doing sensible things. Then connect the micro-ROS agent again and check the IMU data topic. So again, make sure, step at a time, IMU data is making it up into ROS infrastructure. Design and build your robot and customize the configuration file. We'll look at that file here just momentarily. Test the motors and encoders. So he's got a program that will run the motors at quarter speed, full speed, spin, and just make sure that the mechanics work. Then test the LiDAR, make sure you're getting LiDAR back. Then launch the robot bring up and use a keyboard to move the robot. Now, part of this testing the motors and encoder checks that it actually goes forwards when you expected it to go forwards, because if you have your NA and NB backwards, or your quadrature encoder signals backwards, it can go backwards, or it may go forwards, but it tells you it's going backwards, or it comes out through the readings emitted from the test programs. So then you launch the robot bring up, you use a keyboard to move the robot, then you use a gamepad to move the robot, then you launch SLAM and save the map, you launch navigation with a map, and then you write some application software, and then you're done. Simple as that. Number 11 is a doozy. Okay, so let's see if we can bring up the config file. Okay, I'm going to exit this. There we go. Okay, so is that readable? Yeah, I guess so. So this is, in my opinion, the magic that makes Linorobot2 turnkey, is this config file. So it's pretty long, but there's a lot of parameters in a robot. There we go. And so you create a config file. You take one of the existing files like ESP32_Wi-Fi. You rename it according to your robot minibot Wi-Fi.config, and then you start changing the parameters. So you define it as a differential drive robot. You define the motor driver model. Other options could be an ESC motor driver, or a generic 1 or 2 in motor driver. So different models of motor driver interface. You define your IMU. There's some things here that I haven't messed with. You define your motors, max RPM and max operating voltage, and counts per rev for the encoder, and wheel diameter and wheel left-right wheel distance, how many PWM bits there are. So these are all the parameters that you'd be hard coding in. Yeah, you do it with, this is what you do anyway. But the point is that this is how they've made a robot that you don't have to actually code that stuff in code. You just set a parameter in a config file.
That's how you reuse.
Yeah, exactly. There's parameters here to invert the encoder counts. So one of your encoders likely runs backwards because it's on the other side of the robot. Invert the motor direction, same thing. It's not rocket science, but it's, here's where you set the pins, the PWM pin, the motor NA and NB pins. As you say, you'd write your own software to do this, but it comes canned in this.
Normal robot program. They would configure
Yeah.
robot block.
Right.
And then that would have all your pins defined.
Right.
That would have all
Right.
If you don't want any magic numbers,
Right.
code,
Right.
that's what this.
Yep.
that's what it should-
Exactly right.
And then, you have all your functions separated. If you're using C, there's you separated into separate files. You'd have a motor function file, you'd have a sensor file.
Yep.
And so on.
Yep.
So this is just good practice.
Yeah, it is. And here's where you define the Wi-Fi access point list. So currently I've uncommented the Dallas Makerspace section. I've got sections for my cell phone and my home network. You declare the password, the agent IP. So this is the IP that my laptop is at, which if you're using a Raspberry Pi on the robot, then these are don't cares. Except the syslog server might be useful. I don't know. The LiDAR server, LiDAR baud rate, UART number. It'd be serial. Serial would make most sense. USB serial. Yeah. He recommends running at a mega baud. So then you init the pins, and that's it. That's the config file. There's one other config file that you do edit, which is the robot model that tells RViz how to draw the robot. So the width of it and size of the wheels and so forth, just so it draws right. But this is the heart of what gets compiled into the firmware running on the ESP32.
That is the plain view EXF that we're doing for the how it draws the robot.
Yeah. And that's it.
That and you can highlight all the canned hardware, does all the recording you showed.
So before I move on to almost at the end here, any questions on the workflow for making a robot, a LiDAR robot? Okay. So the good, the bad, and the ugly. The good, it's map-based navigation, very powerful. Variety of supported motors and drivers and sensors. Good tools for logging and analyzing data from your robot in ROS. ROS is built around composable nodes, and with the idea that this is kind of a design pattern, architectural pattern that nodes or components should do one small thing well and should be able to be composed into a system. You see this architectural pattern in Linux where you've probably seen text processing pipes in Linux, where you've got cat file name piped to cut -F2 to pick out the second field, piped to sort, piped to unique to get rid of duplicates, piped to T to write some of it to a file and some of it to stand out. That's another example of a composable system. And ROS is a composable system by design. And so the idea is that all of these packages, I suppose, should do one small thing well and be able to be reused in a variety of contexts. So that's pretty neat. Bad and the ugly, there isn't a branch labeled Jazzy. I think that's bad. ROS releases annually, and the latest version is called Jazzy, the name of the release. And this Thomas Chu's repo works with Jazzy. I'm using it here, but there's no branch named Jazzy. Worse than that, ROS2 and MicroROS, currently based on DDS, which may not work with some home routers, like my Eero6, won't pass ROS messages. Sucks. DDS is a network protocol that sits on top, above UDP, and that ROS uses to pass messages. There are alternatives, but they have some caveats. Thomas Chu's forks, I'm using Thomas Chu's fork here, and I've been feeding updates and fixes into his fork, have diverged from the upstream, the main Linorobot2 repos, and the one Gemino is busy upgrading the main Linorobot repos to do simulation in Jazzy with the new Gazebo harmonic release, while I'm down here with Thomas in his repo getting it working on Jazzy, getting hardware working on Jazzy. That's really ugly, and they need to be converged. So this is where my video here is part of my plan for world domination. These are my creds. This is my presentation to the broader community as well as you guys. But I think Linorobot has a lot of promise, a lot of value as a easy, almost turnkey software system for doing map-based navigation and your own apps, interacting with maps, with map-based navigation, for doing a whole variety of things. And there is a significant community. There are something like 700 subscribers to the Linorobot email list. So a lot of people over the years have at least subscribed to the email list. And I think it's time that this package got sort of like a little love, a little care, a little bringing up to date and releasing on Jazzy with both simulation and working on hardware. That's where I think it needs to go. Yep, yeah, absolutely. And finally, every slide set should end with a call to action and a picture of a bridge. So here you go. Why should you use Linorobot2 with ROS 2 navigation? Because it makes you more powerful. So I invite you to come and join me exploring Linorobot2 at Airbnbs. And all my robots, including Mobot, are soon going to run Linorobot2, because it just gives you so much power without you having to understand how to put the components together in the nav2 stack, and try and adapt a TurtleBot config, perhaps, or, you know, it's almost turnkey, and there's no programming required, at least as far as getting it to work under RViz. Now, I will state Doug's caveat, which I 100% agree with you, that this ROS stuff is all great, and if it works, you're in Fat City, but if it doesn't work, you might be in a very deep, dark place. And I think that's a fair comment too.
Put one under a tree, so.
Okay, hold that thought, and because I want to wind up my talk here. Everybody's been super patient, and I really appreciate. So you can say more about that, but the slide set will be on the web. Here are the references to Thomas Chu's repo and wiki for the two repos, Linorobot hardware and Linorobot2. The automatic Edison tutorials, really recommend them if you want to get more in, understand different aspects of ROS. There must be 100 tutorials out there. It's just, the guy is prolific. Yeah, and good stuff. And I pointed to the nav2 Commander API. And then a note that you can set up a syslog server to record logs. And one thing I didn't do was set up over-the-air firmware upgrade, but you can, you know, with a ESP32, you can do OTA and upgrade your firmware. So it's pretty cool. So that's it. Thank you very much, everybody, for your attention and interest.